from the equilibrium constant, we can calculate the unknown concentration of reactants or products once equilibrium has reached, which is temperature is constant. So we can predict the directions of the reactions. We use QC instead of KC if the reaction has not reached the equilibriums. So we can compare the value of QC and KC to predict the directions of the reactions. When QC is equal to KC means that the reaction is at equilibriums. While if QC is less than KC means that reaction will proceed to the right, means that favor to the product side. While if QC is more than KC means that reaction will proceed to the left, means favor to the reactant. Okay, let's we try to solve these questions. Given that at the start of the reaction there are 0.249 moles, while this one hydrogen is equal to 3.21 times 10 power negative 2 moles, and for ammonia is equal to 6.42 times 10 power negative 4 moles. So first we need to calculate the concentrations of each species involved in the reactions. So the concentrations of nitrogen is equal to 0.249 mole divided by, given that the volume is 3.5 liter, so equal to 0.0711 molar. So for hydrogen, and for ammonia. So K prime or QC is equal to the concentrations of the products divided by the concentration of the reactant. So we just substitute into the equations. NH3 is equal to 1.83 times 10 power negative 4 divided by 0.0711. So from the calculation, we get the value of Kc is less than Kc, which is given that Kc is equal to 1.2. Means that when the Qc is less than Kc, means that the reaction will proceed to the right. Means that favor to the products. The net result will increase in the concentrations of the ammonia and decrease in the concentrations of the nitrogen and hydrogens. So the net reaction will proceed from the left to the right until equilibrium is reached. Okay, calculating equilibrium concentration. Consider the following reactions. What is the concentration for each substance at equilibrium is the initial concentration of acetylene is equal to 0.355 molar and hydrogen is equal to 0.526. So we use ICE method to solve this equation, initial change and equilibriums. So firstly we need to form a tables and put the value in the tables. So 0.335, this one 0.526, and for product is 0 at the initial. And then we use X to represent the change, which is negative, means that the reactant will become negative after the reactions and the product will become positive. So the change after the equilibrium, the concentration is equal to 0.335 minus X. For this one 0.526 and X. So from there we can calculate the K. K is equal to X over 0.335 minus 2x, 0.526 minus 2x is equal to 0.99. So using the quadratic equations, we can solve these equations and we can get two values of x. X is equal to 0.099 and 1.77. So we will ignore this value, since that when you minus 0.335 to 1.77, you can get negative value. So we just use this value to calculate the concentrations. So from the calculation, we can get the concentration of each species involved in the reactions. According to Lee-Cattelius principles, if a system at equilibrium is disturbed by a change in temperature, pressure, volume, concentrations of the components, the system will shift its equilibrium position so as to counteract the effects of the equilibriums. Lee-Cattelius principles help us to predict the effect of changing the conditions in a chemical reactions. If an external stress is applied to a system at equilibriums, the system adjusts the stress as the system reaches a new equilibrium positions. Effect of concentrations of equilibriums. What happens if we increase the concentrations of the reactant? For example, A. If we increase the concentration of the reactants, the positions of equilibrium will move to the right, which is more reactant A will react with B to producing a product C and D. In practical, this is useful way of converting the maximum possible amount of B into C and D, which is this is advantageous. For example, if B is relatively expensive materials, whereas A is cheap and plentiful. For B, when we decreasing the concentrations of A, means that the positions of equilibrium will move from the right to the left, which is more C and D will react to replace A that removed from the reactions. This is essentially what happens if one of the product is removed as soon as it is formed. For example, if C is removed in this way, the positions of equilibrium will move to the right to replace it. And it is continually removed, the equilibrium position shift further and further to the right, effectively creating a one-way irreversible reactions. When iron tricyanide dissolved in water, the red solutions will appear due to the presence of hydrated thiocyanate ion. What happens when we add thiocyanate? Okay, when we add thiocyanate, the equilibrium will shift from the right to the left. The same thing happens when we add the iron trinitrate to the original solutions. The color will also be deepened because the addition of the ferrum ions, so that the equilibrium will shift from the right to the left. Effect of pressure on equilibriums. The pressure only involved if the reactions involving gas, although not necessarily all species in the reactions in the gas phase. Okay, consider these reactions. In this case, there are 3 moles of the gas on the left hand sides of the equations, but only 2 on the right. Okay, by forming more C and D, the system causes the pressure to reduce. Increasing the pressure on the gas reaction shift the positions of equilibriums toward the sides with the fewer moles of gas molecules, which is change in pressure ordinarily not affects the concentrations of liquid and gas phase since they are incompressibility. The concentration gas greatly affects by the change in pressure. For the ideal gas equation, PV is equal to nRT. So P is equal to N over VRT, which is P and V are related to each other inversely. The higher the pressure, the lower the volume, and vice versa, which is N over V is the concentrations, mole per liter, and varies directly with pressure. Okay, conversely, when we decrease the pressure, the equilibrium will move from the right to the left. If there are same number of moles on the both sides of the equilibrium reactions, increasing the pressure has no effect on the positions of the equilibriums. Adding or remove a gas reactant or products. Adding a products makes QC more than KC, so that this will change in reverse directions towards the reactants. Adding an inert gas to the constant volume reaction mixture does not result in shift. And changing the volume of the system, if the volume is reduced, a net change occurs in the directions that produce fewer moles of gas, while when the volume is increased, the change occurs in the directions that produce more mole of gas. Temperature change. When the temperature is increased, the positions of equilibrium will move so that to reduce the effect of temperature change. If the temperature increase and higher than the temperature of the system in equilibriums, the positions of equilibrium will move so that the temperature is reduced again. To cool down, back reaction is occur, which is extra heat is absorbed. The positions of equilibrium will move to the left, which heat is absorbed. Then the new equilibrium mixture contain more A, B, and less C and D. Okay, so if the goal is to maximize the amount of C and D, increasing the temperature on a reversible reactions in which a forward reaction is exothermic is a poor approach. So the effect of temperature on equilibrium is increasing the temperature of system in dynamic equilibrium favor the endothermic reactions. So the system counteract the change by absorbing the extra heats. And decreasing the temperature of a system in dynamic equilibrium favor the exothermic reactions. Means that the system counteract the change by producing more heat. Effect of catalyst on equilibriums. According to Lee catalyst principle, the catalysts do not affect the chemical equilibriums. Catalysts only speed up the forwards and back reactions to the same extent, and the adding catalyst does not affect the relative rates of the two reactions and cannot affect the positions of the equilibriums. Catalysts just speed up the rates at which a reaction reaches dynamic equilibriums but remain constant. Okay, considering the following reactions, which is it is possible to change the pressure of the system without changing its volumes. Suppose that the nitrogen dioxide and dinitrogen tetroxide in equilibrium system is contained in the stainless steel vessels whose volume is constant. So we can increase the total pressure in the vessel by adding inert gas such as helium in the equilibrium systems. By adding the helium in the equilibrium mixture at the constant volume will increase the total gas pressure and decrease the mole fractions of both nitrogen dioxide and dinitrogen tetroxide. Okay, since that the partial pressure of each gas given by the product of the mole fractions and the total pressure does not change at the constant volume, so that it's not affect the equilibrium constant. Increasing the temperature will favor the endothermic reactions, means that the reaction will shift from the left to the right of the equilibrium equations, means that the concentrations of the dinitrogen tetroxide will decrease and the concentrations of the nitrogen dioxide will increase. Conversely, the temperature decrease will favor the exothermic reactions, means that the system will shift from the right to the left of the equilibrium equations, so that the concentrations of nitrogen dioxide will decrease and the concentrations of dinitrogen tetroxide will increase. Consequently, the equilibrium constant Kc will increase when the system is heat and decrease when the system is cool. A change in temperature can alter the value of the equilibrium constants. For endothermic reactions, means that the system will absorb the heat, which is delta H is positive. So increasing the temperature will favor the reactions toward the products. Meanwhile, for the exothermic reactions, mean that the system will release the heat, which is delta H is negative, means that increasing temperature will favor the reactions towards the reverse directions, means that favor to the reactant.